In a perfect world, our data would follow the classical assumptions of linear regression. The textbook ideal posits that errors are homoskedastic, meaning they have constant variance, and are completely independent from one another. This is often summarized as the assumption of spherical errors, where the error covariance matrix is simply an identity matrix scaled by a constant variance. However, real-world panel data rarely conforms to this ideal. We frequently encounter heteroskedasticity, where the variance of errors differs across units. For instance, large firms might exhibit much more volatile behavior than smaller ones. Furthermore, cross-sectional correlation is common, particularly when a market-wide shock impacts all entities in the panel simultaneously. The critical consequence of these real-world complexities is that while using standard ordinary least squares, or OLS, may still yield unbiased coefficients, the calculated standard errors will be incorrect. This inaccuracy invalidates our t-tests and can lead to false conclusions about the statistical significance of our variables. This decision tree is your guide to selecting the most appropriate estimator for your panel data, starting with the fundamental dimensions, the number of units, n, and time periods, t. If you have what we call a micro panel, characterized by many units but very few time periods, large n, small t, your best course of action is typically to use fixed effects or random effects models, implemented in Stata with xtgls. These are excellent for addressing unobserved heterogeneity. However, if you are working with a macro panel, meaning your time dimension is relatively large, t is greater than or equal to n, then you enter the domain of Generalized Least Squares, or GLS. The next crucial question here is whether your errors are independent. If they are, pooled OLS might be considered, though it's quite rare for real-world macro panels. More often, you'll encounter a complex error structure, indicating that your errors are not independent. In such cases, GLS is the Goldilocks solution. It's ideally suited for complex error structures, especially when you have enough time periods, typically 15 or more, to reliably estimate those underlying correlations, leading to more efficient and accurate estimates.
Here, we compare key Stata commands for panel data estimation, outlining their underlying assumptions and best applications. The regress command serves as our basic benchmark, assuming independently and identically distributed errors, ideal for initial comparisons. For micropanels, characterized by many units but few time periods, the xtgls command with fixed or random effects is the go-to. Its strength lies in handling unobserved heterogeneity, like individual specific effects represented by alpha sub I. When dealing with macro panels, many time periods, and a smaller number of units, xtgls becomes crucial. This command explicitly models a complex error covariance matrix, omega, to account for both heteroskedasticity and correlation. Finally, xtpcse offers a robust alternative for complex errors. It applies OLS coefficients, but provides corrected standard errors, particularly useful when the number of units is large relative to time periods, helping to mitigate potential overconfidence from FGLS. Choosing the right command ensures more efficient and reliable estimates, which we will explore further.
The standard OLS estimator, as you see in the formula, gives equal weight to every single data point. It inherently treats all observations as equally informative, essentially giving each a weight of 1. In contrast, the GLS estimator introduces a crucial new component, the precision matrix, denoted as omega inverse. This matrix is the inverse of the error covariance matrix, which we'll explore in more detail next. The precision matrix acts as a sophisticated weighting mechanism. It intelligently downweights observations that have high variance, essentially identifying them as noisy data points that are less reliable. Conversely, it upweights observations with low variance, giving these more precise data points greater influence in determining the regression coefficients. By accounting for this varying reliability, or noise, in the data, GLS achieves the BLUE property, Best Linear Unbiased Estimator. This means it produces the smallest possible standard errors among all linear unbiased estimators, leading to more efficient and reliable statistical inferences. The error covariance matrix, Omega is central to generalized least squares, as it fully captures the complex structure of our regression errors. This visual representation helps us understand its components. On the main diagonal, you see the variances for each individual unit, like firm A. If these elements differ, we have heteroskedasticity. Within each firm's diagonal block, the off-diagonal elements show autocorrelation, indicating how errors for a firm are correlated across time, often following an AR1 process with a fading memory. The off-diagonal blocks, like sigma AB, represent cross-sectional correlations, capturing how errors between different firms are related. To successfully implement feasible generalized least squares, we rely on three key assumptions. First, strict exogeneity, meaning errors are uncorrelated with our independent variables. Second, the precise structure of omega must be correctly specified. And critically, for the most comprehensive FGLS models, the number of time periods t must be large enough to reliably estimate all these parameters, generally requiring t to be greater than or equal to m. The interpretation of the coefficients, the betas, in a generalized least squares model is largely similar to ordinary least squares. They represent the change in the dependent variable for a one-unit change in an independent variable, holding other factors constant. However, if you observe drastic changes between your OLS and GLS coefficients, this could be a red flag, indicating potential model misspecification. The primary benefit and the main reason for employing GLS lies in its impact on the standard errors. When the model is correctly specified, GLS standard errors will be smaller and more efficient than those obtained from OLS, leading to more precise inference. A crucial warning, though, feasible generalized least squares can sometimes be optimistic, meaning it may underestimate the standard errors. This is particularly true when the number of cross-sectional units, n, is large relative to the number of time periods, t. In such scenarios, it's advisable to consider using xtPCSE, or panel-corrected standard errors, as a more robust alternative. Let's break down the xtgls command, central to generalized least squares in Stata. The basic syntax involves your dependent and independent variables, followed by powerful options for modeling the error structure to achieve efficient estimates. The panels option controls the variance. Panels IID assumes constant variance, similar to OLS. Panels heteroskedastic allows each panel to have its own distinct error variance. For cross-sectionally correlated groups, panels correlated models this, but importantly, it requires that your number of time periods, t, is greater than or equal to your number of units, n. The core option handles time series correlation. Core independent assumes no serial correlation. Core AR1 models a common first-order autoregressive process with a shared autocorrelation coefficient, rho. For greater flexibility, Core PSAR1 allows each panel to have its own specific rho. These options enable precise tailoring of your xtgls model to the complex aerodynamics of your panel data. Before diving into complex panel data analysis, it's crucial to properly prepare and structure your dataset. The first step involves declaring your panel structure to Stata using the xtset command. You specify the panel identifier variable, like an ID, and your time variable. This command is vital as it not only sets up your data for panel operations, but also reports whether your panel is balanced or unbalanced. A balanced panel means every unit has observations for every time period, while an unbalanced one has gaps. Next, it's essential to check the balance of your panel, especially if you plan to use advanced options like panels correlated in xtgls. This particular option requires a strongly balanced panel, meaning there are absolutely no missing years for any individual unit. If your data has these gaps, the tsfill command is your tool. It will automatically fill in missing time periods with observations containing missing values for other variables, ensuring your panel is strongly balanced and ready for robust estimation methods. Building on our discussion of fundamental generalized least squares estimation, modern versions of Stata, specifically 18,
19, and the State of Now releases introduce advanced options that offer even greater flexibility and precision. First, the core unstructured option, available with Stata Now, allows for fully unrestricted autocorrelation within panels. While highly flexible in modeling complex temporal dependencies, it's important to remember that this consumes a significant number of degrees of freedom, requiring sufficient data to ensure reliable estimation. Next, the N-K option provides control over the normalization of standard errors. By normalizing standard errors by N-K instead of just N, we ensure consistency with how other statistical software packages or older literature might present results, which is crucial for replication and comparability. Finally, IGLS, or iterated GLS, represents an optimization feature. Unlike standard FGLS, which might stop after a set number of steps, IGLS iterates until the coefficient estimates fully converge. This iterative process often leads to estimates that align with maximum likelihood estimates, offering superior asymptotic efficiency when the model is correctly specified. We begin our practical application by exploring the data from StataPress, specifically the Invest2 dataset. First, we load the data and formally declare its panel structure using the xtsetCompanyTime command. A fundamental first step in any panel data analysis is always data visualization. We employ the xtline command to generate a time series plot for the investment variable across each company. This visual inspection immediately highlights a critical characteristic of our data. General Electric's investment profile demonstrates significantly greater volatility compared to the other companies. This stark difference in variance is a clear indicator of groupwise heteroskedasticity, a common issue in real-world data that violates the standard assumptions of ordinary least squares. This visual evidence will guide our modeling choices in the subsequent steps. To account for the heteroskedasticity we observed in the previous step, we run the xtgls command with the panel's heteroskedastic option. This instructs Stata to allow the error variance to differ across each company in our panel. The output confirms that we are performing a cross-sectional time series FGLS regression and that the panels are indeed specified as heteroskedastic. Currently, we are not modeling autocorrelation. The most crucial takeaway here is that our standard errors for market and stock have now been adjusted for this groupwise heteroskedasticity. Essentially, the model trusts firms with less volatile investment patterns more, giving them greater influence in estimating the regression coefficients, which leads to more efficient and reliable standard errors compared to a standard OLS model. Building on our previous step, we now address autocorrelation by adding the core AR1 option to our xtgls command. This instructs Stata to model the errors as following a common first-order autoregressive process across all panels, while still accounting for heteroskedasticity. The output prominently displays an estimated common AR1 coefficient, or rho, of 0.865. This high and statistically significant value indicates a strong positive serial correlation, meaning that a firm's past investment strongly predicts its current investment. Explicitly modeling this persistence is crucial because it removes a significant source of bias from our standard errors. By doing so, we ensure our inferential conclusions about the effects of variables like market and stock are more accurate and reliable, as this accounts for the inherent time dependence in the data. We've now arrived at the most comprehensive model, often referred to as the Parkes method or Parkes-Commenta method. This is achieved in Stata by running xtgls with both the panels correlated and core R1 options. This powerful heavy lifter model simultaneously addresses three critical issues in panel data. It accounts for group-specific heteroskedasticity, time series autocorrelation, and crucially, cross-sectional correlation between your units. The output clearly states that the panels are heteroskedastic with cross-sectional correlation and also shows the number of estimated covariances. However, using the panels correlated option comes with a very strict and vital constraint. The number of time periods, t, must be greater than or equal to the number of cross-sectional units, n. If t is less than n, the error covariance matrix becomes singular, meaning it cannot be inverted, and the method will simply fail.
This is a critical consideration to keep in mind when applying the Parks method.
The problem we've noted is that when the number of units, n, is large relative to the number of time periods, t, feasible generalized least squares, or FGLS, can become overconfident. This means it might produce standard errors that are too small, leading to incorrect inferences about the significance of our variables. To address this small t, large N challenge, Beck and Katz in 1995 proposed the use of panel-corrected standard errors, or PCSE. In Stata, this method is implemented via the xtpcse command, as shown with an example of estimating investment with market stock, allowing for AR1 correlation. It's important to understand the fundamental difference between xtgls and xtpcse. While xtgls attempts to modify the actual coefficient estimates by weighting observations to achieve greater efficiency, xtpcse takes a different approach. It preserves the simpler ordinary least squares coefficient estimates, but then robustly adjusts the standard errors to account for the complex error structure. This distinction leads to a clear recommendation rule. If your dataset is wide, meaning the number of units, n, is greater than the number of time periods, t, then xtpcse is generally the more robust choice. Conversely, if your dataset is tall, with significantly more time periods than units, t much greater than n, then xtgls is often the more efficient and appropriate method. We shouldn't just assume heteroskedasticity is present. We should always test for it to justify our model choice. A standard and powerful method for this is the likelihood ratio test. The process begins by estimating a restricted model, which assumes homoskedasticity, meaning constant error variance. In Stata, this is done using xtgls with the panel's IID option, and we store its estimates. Next, we run a full model that relaxes this assumption, allowing for heteroskedasticity, using xtgls with panels heteroskedastic. We also store these estimates. The core of the diagnostic is then to perform a likelihood ratio test using LR test to compare these two models. If the test yields a statistically significant chi-squared statistic, typically with a p-value less than 0.05, it provides strong evidence against homoskedasticity. In such a case, we conclude that heteroskedasticity is present and should adopt the full, more flexible model. Conversely, if the test is insignificant, we favor the simpler, restricted model. Additionally, after any estimation, it's good practice to perform a residual check by predicting and examining the residuals, which can reveal further patterns or issues. To summarize our discussion on achieving efficiency in panel data analysis, let's look at some key best practices. You should use xtgls for macro panels, which are characterized by a relatively large number of time periods, typically 15 or more, and a smaller number of cross-sectional units. Before modeling, always make sure to visually inspect your data for issues like heteroskedasticity, using commands such as xtline. Furthermore, if your panel dataset has many units but fewer time periods, meaning n is greater than t, xtpcse is generally the safer and more robust choice to handle complex error structures. Conversely, there are practices you should not follow. Do not use the panels correlated option with xtgls if your time dimension is smaller than your cross-section dimension, t less than n. This will lead to a singular error covariance matrix, making the estimation impossible. Finally, it is crucial not to ignore serial correlation in time series data. Failing to account for it will result in biased standard errors and potentially invalid inferences. Adhering to these guidelines will significantly improve the reliability and efficiency of your panel data estimations.